This is an appendix to Lecture 16 in the series General Topology. For those of you who already have my notes, this is a correction to Theorem 16.8. Special thanks to YouTuber Recursive for pointing out a flaw. Okay, so we're going to start by looking at a consequence of the density of the rational numbers in the reals. So let the interval from R to S be an open interval. In the real line. Then the open interval Rs is the set of all points x such that x is strictly greater than r and strictly less than s. So it does not include the real number r nor the real number s. Now, as the set of rationals is dense in R, there exists a rational number, a sub 1, such that a sub 1 is strictly less than r, strictly greater than r, and strictly less than s. We can continue injecting rational numbers ad infinitum, producing a decreasing sequence of rational numbers where each rational number in the sequence is strictly less than r and is strictly greater than r and strictly less than the one that precedes it. So that we can get as arbitrarily close as we like to the real number r by means of a decreasing sequence of rational numbers. In the language of limits, we have that the limit as n approaches infinity of the sequence a sub n is the real number r. Similarly, there exists a rational number b such that b is greater than r and less than s. We'll call it b sub 1, b sub 1. Once again, we can produce an increasing sequence this time of rational numbers strictly less than the real number s, so that the limit as n approaches infinity of the sequence b sub n is the real number s. And so the interval having real endpoints r and s is a union of intervals of the form ab, where a and b are rational numbers and a is strictly less than r, strictly greater than r, which is strictly less than b, and b is strictly less than s. So every open interval in the real line can be expressed as a union of open intervals having as its endpoints rational numbers. So now we can state a more important result, and I'll state this as a lemma. The set of open rectangles script R consisting of the product of open intervals where the endpoints of those intervals are rational numbers is a countable basis for the product topology on the real plane. All right, so now we need to prove this statement. So let script B be the set of open intervals having as its endpoints real numbers, and let script I be the set of open intervals having as its endpoints rational numbers. Now we already know that the collection script B is a basis for the standard topology on the real line, that is the ordered topology. Now for every open interval AB in the collection script I, that interval is in the collection script B. So every open interval in the collection script I is open in the topology generated by the collection script B. Now every interval RS in the collection script B is the union of open intervals of the form AB, where A and B are rational and A is strictly greater than R, strictly less than B, and B is strictly less than S. So every interval in the collection script B is open in the topology generated by the collection script I. And so both the collection script B and script I generate the same topology, on the real line, namely the order topology. Okay, so so far we've demonstrated that the collection script I is a basis for the order topology on the real line. We now need to show that this basis is a countable one. So define a function f mapping ordered pairs of rational numbers into the set of all open intervals having as its endpoints rational numbers by f of the ordered pair AB generates the open interval from A to B. Then clearly, for every open interval AB in the collection script I, there exists an ordered pair AB in the set of ordered pairs of rational numbers, such that f of AB is the open interval from A to B. So the function f is surjective. Now suppose that f of the ordered pair AB is equal to f of the ordered pair CD. Then the open interval from A to B is the same as the open interval from C to D, so that the endpoints must be equal. That is, A is equal to C and b is equal to d. And so the function f is injective. And so the function f, again, a map from ordered pairs of rational numbers into the set of intervals having as its endpoints rational numbers, is a bijection. Now, as the set of ordered pairs of rational numbers is a product of the rational numbers with itself, that is, it is a finite product of countable sets. It is countable. We have already demonstrated in a previous lecture that the set Q of rational numbers is countable, so a finite product of countable sets is countable. So there exists a bijection, which we'll call G, mapping the set of positive integers into ordered pairs of rational numbers. And so the composition of f with g is a map from the set of positive integers into open intervals having as its endpoints rational numbers. And this composition is a bijection, as it is the composition of two bijective functions. And so the collection script I, consisting of open intervals having as its endpoints rational numbers, is countable. And so script I is a countable basis for the order topology on the real line. So the collection script R, being the product of the basis element I for the real line, is a basis for the product topology on the real plane. Further, this collection script R is countable, as it is a finite product of countable sets. So we have demonstrated that the collection script R, being the collection of open rectangles, each produced as a product of open intervals, parallel to the axes, where the endpoints are rational, is a countable basis for the product topology on the real plane. All right, now, as this collection script R is a basis for the real plane with the standard topology, every open subset U in the real plane is a union of some elements, or as I'll call them, some rectangles, in the collection script R. Further, this union is necessarily countable as the basis script R is itself countable. So a union of sets in a countable set must be countable. All right? Okay, so let me quickly remind you of the statement of the theorem that precedes the one of interest, since we're going to use it in the proof of the theorem of interest. Let Y and Z be topological spaces, and let G, being a map from the space Y into the space Z, be continuous. If X is a measurable space, and the function f mapping the measurable space X into the topological space Y is measurable, then the composition of G with F, being a map from the measurable space X into the topological space Z, is measurable. All right, so now the theorem of interest. Let U and V be real measurable spaces. Correction, be real measurable functions on the measurable space X. Let Y be a topological space, and let the function G, mapping the real plane into the topological space Y, be continuous. Then the function H, being a map from the measurable space X into the topological space Y, defined by H of X is G of the ordered pair U of X, V of X. This function H is measurable. Okay, so now the proof. First, notice that U and V are both real measurable functions on the measurable space X. So U is a measurable function from the measurable space X into the real line, as is V. So as U and V are measurable functions, the inverse image under either of these maps of any open set in the real line is a measurable set. Now let the function f be a map from the measurable space X into the real plane, and let it be defined by f of X is the ordered pair U of X, V of X. Then the function H is the composition of G with F, and this composition by the previous theorem is measurable. if the function f is measurable. So it remains to show that the function f is measurable. So let R be an open rectangle in the countable basis script R. Then the rectangle R is the product of two open intervals in the real line. So the inverse image under the map F of the rectangle R is the inverse image under the map F of the product of two open intervals in the real line. This is the same as the intersection of the inverse image under the map U of the interval I sub 1 with the inverse image under the map V of the open interval I sub 2. Again, U and V are measurable functions, so the inverse image of an open set in the real line is a measurable set, and so the inverse image of a rectangle in the plane is a countable intersection of measurable sets, and is therefore measurable. Now, every open set V in the real plane is a countable union of such rectangles. Which will denote R sub I. And so the inverse image under the map F of any arbitrary open set in the plane is the inverse image of a countable union of rectangles. This is the same as a countable union of the inverse image of rectangles. And so the inverse image of any arbitrary open set in the plane is a countable union of measurable sets. And is therefore measurable. And therefore the function h, being the composition of a continuous function with a measurable function, is measurable. All right, so that completes the proof.